Right now, as you're listening this, something remarkable is happening beneath your feet. Earth is spinning. It's been spinning for billions of years. Day follows night. The sun rises in the east. The stars trace their familiar paths across the sky. Everything feels steady, permanent, fixed in place. But here's the thing, it's not. Earth isn't a rigid ball locked into one position forever. It's a dynamic world, a rotating planet influenced by forces we rarely think about. Forces from deep inside its core, forces from the oceans and atmosphere, even forces from the moon and sun, millions of kilometers away. And recently, scientists noticed something, a shift, a small but measurable change in how our planet moves through space. This isn't about earthquakes. It's not about continental drift or tectonic plates. This is something more subtle, more global. A change in Earth's orientation itself, the way it spins, the way it balances in the void of space. It's the kind of shift most people will never feel. You won't see it in the sunrise. You won't notice it in your daily life. But it's there, recorded in instruments that measure motion with precision, far beyond what our senses can detect. We live with this quiet assumption that the ground is stable, that the planet we stand on is unchanging. And in many ways it is. But in other ways, Earth is constantly adjusting, responding to changes in how mass is distributed across its surface and deep inside, responding to the pull of gravity from celestial bodies light years away. It's a conversation between layers, between systems, between Earth and the cosmos around it. Understanding this shift means stepping outside our everyday experience. It means thinking about the planet not as a fixed stage, but as a moving participant in a larger dance, a dance governed by physics, by conservation laws, by the slow redistribution of mass and energy across a spinning world. So let's explore what happened. Let's understand what this shift really means, not just for the planet, but for how we think about stability, change, and our place in the universe. If you're enjoying this, consider subscribing. It really helps the channel. Let's start with something important. When we talk about an Earth shift, what exactly do we mean? The word shift gets used a lot. Sometimes it refers to earthquakes, sometimes magnetic field changes, sometimes continental drift. But what we're focusing on here is something different, something more fundamental. We're talking about a change in Earth's orientation, in how it rotates in space. Think of it this way. Earth is a spinning top. It turns on its axis. That axis points in a certain direction relative to the stars. And over time, that direction can change. Not quickly, not dramatically, but it changes. Sometimes the speed of rotation adjusts slightly. Sometimes the axis tilts a bit differently. These are subtle shifts, but they're real, and they tell us something important about how our planet works. Now, here's why this matters. When we measure these changes, we're not comparing Earth to itself. We can't just look at landmarks on the surface and say, oh, this moved. Because everything on the surface moves together with the planet. Instead, we have to look out, way out, to distant points in space that don't move with Earth, points that give us a fixed reference. Scientists use quasars for this. Quasars are incredibly distant objects, so far away that their positions appear essentially fixed from our perspective. By measuring Earth's position relative to these cosmic markers, we can detect tiny changes in how the planet spins, changes measured in fractions of a degree, changes that accumulate over years or decades, changes that would be invisible to the naked eye, but are clear in the data. This kind of shift is different from what happens during an earthquake. An earthquake moves pieces of the crust. It releases energy stored in rocks. It can be violent and sudden, but it doesn't change the planet's overall rotation. It doesn't tilt the axis. What we're talking about is more subtle. It's a redistribution of mass that affects the entire planet's balance. Imagine a figure skater spinning with arms extended. When they pull their arms in, they spin faster. When they extend them again, they slow down. Earth does something similar. When mass moves around on or inside the planet, the rotation adjusts to conserve angular momentum. Let me give you an example. When ice melts at the poles and flows into the oceans, that's a redistribution of mass. Ice that was concentrated near the axis of rotation spreads out across the ocean basins. That changes how Earth's mass is distributed, and when mass distribution changes, the rotation changes too, not by much, but by a measurable amount. Over time, these small changes add up. They become trends, patterns, shifts that tell us something about what's happening deep inside our world and across its surface. So when we say Earth has shifted, we mean its rotational behavior has changed in a way that's detectable with precise instruments. We mean the planet's orientation in space has adjusted, not because of some external force pushing it around, but because of internal changes in how mass is arranged. It's a global phenomenon. It affects the whole planet at once, and it's been measured and confirmed through multiple independent methods. This is important because it shows us Earth isn't static. It's dynamic, always responding, always adjusting. The shift we're discussing is part of that ongoing process, a recent example of how a planet maintains its balance as conditions change. By understanding what kind of shift we're talking about, we can dig deeper into why it happened, how it was detected, and what it means for our understanding of Earth as a living, moving world. Now let's think about why this feels so strange. Why does a planetary shift seem almost impossible to believe? The answer has to do with how we experience the world, how our senses work, and how our brains interpret motion. Human beings evolved to detect movement across the landscape. A predator approaching, a fruit falling from a tree, wind moving through grass. We're really good at noticing when things around us change position, but we're terrible at detecting motion we share. When you're sitting in a car moving at a constant speed on a smooth road, you don't feel the motion, you feel at rest. Your body has no way to sense the velocity, only changes in velocity register, acceleration, deceleration, turns. But steady motion, nothing. Earth's rotation is like that car. We're moving with it, spinning at over 1,600 kilometers per hour at the equator, but we don't feel it. There's no wind in our face, no sense of speed, because the atmosphere moves with us. The ground moves with us. Everything we can touch or see shares that motion. So to our senses, it doesn't exist. The same goes for Earth's orbit around the Sun. We're traveling through space at about 30 kilometers per second. That's fast, really fast. But we feel none of it. The motion is smooth and constant. There's no friction, no air resistance, no landmarks rushing past. So our brains register it as stillness. For most of human history, this led people to believe Earth was truly stationary, that the sun and stars moved around us. It made sense. It fit the evidence our senses provided. It took centuries for humanity to accept that Earth moves. The idea faced resistance. It contradicted experience. It felt wrong. Even when the math worked out, even when observations supported it, people struggled with the notion because motion on this scale doesn't show up in daily life. You can't see the planet rotating by looking at the ground. You can't feel the orbit by standing outside. The evidence has to come from careful observation of the sky, from tracking how stars and planets appear to move, from building models and testing predictions. And if it was hard to accept that Earth moves at all, imagine how much harder it is to accept that Earth's motion can change, that the rotation can speed up or slow down, that the axis can shift. These are even more abstract, even more removed from sensory experience. A shift in rotation doesn't make the sun rise in a different place tomorrow. It doesn't tilt buildings or shake the ground. It's too small for that, too gradual. It unfolds over years, decades, timescales that blur into background noise for human perception. This is where instruments come in, tools that extend our senses, that measure motion we can't feel, position changes we can't see. Over the past century, technology has given us the ability to track Earth's orientation with incredible precision. We can measure changes in rotation speed down to milliseconds per day. We can detect shifts in axial tilt, smaller than the width of a human hair, as seen from thousands of kilometers away. These measurements reveal a planet in constant subtle motion, a world that's always adjusting its balance. But here's the thing. Even when we see the data, it still feels counterintuitive. Our brains didn't evolve to think about planetary dynamics. We don't have built-in intuition for conservation of angular momentum or mass redistribution on a global scale. So when scientists say Earth's orientation has shifted, part of us wants to ask, how is that possible? The ground feels solid. The sky looks the same. Nothing in our immediate environment hints at this kind of change. That gap between what we feel and what instruments measure is worth sitting with for a moment. It reveals something about the limits of human perception, about how much of the universe operates beyond our direct awareness. We trust scientific instruments because they access a reality our senses can't reach. They make visible what's invisible. They make measurable what's unfelt. And in doing so, they show us a world far more dynamic than our intuition suggests. The recent shift in Earth's orientation is one of those things. Real, measurable, confirmed by multiple independent methods, but completely absent from everyday experience. Understanding it requires accepting that our planet is not the fixed foundation we feel it to be. It's a moving, changing body, one that responds to forces both internal and external, one that maintains balance through constant adjustment rather than rigid permanence. So how does a planet rotate in the first place? What physical principles govern that motion? And how can rotation change over time? Let's build a framework for understanding these questions. We'll keep it simple, no complex equations, just the core ideas that make planetary motion make sense. Start with this. Anything that spins has something called angular momentum. Think of it as rotational inertia, the tendency of a spinning object to keep spinning. Once something's rotating, it wants to continue rotating at the same speed and in the same direction. To change that rotation, you need to apply a force, a torque, something that pushes or pulls in a way that affects the spin. Earth has a lot of angular momentum. It's a massive object spinning once every 24 hours. That's a huge amount of rotational energy. You can't just stop it or speed it up easily. Any change requires moving mass around or applying external forces over long periods of time. And here's the key principle. In the absence of external torques, angular momentum is conserved. That means if the total angular momentum of a system stays constant, but mass redistributes within that system, the rotation rate has to adjust to compensate. Let me give you an example. Remember that figure skater I mentioned earlier? When they spin with arms extended, they rotate at one speed. When they pull their arms in toward their body, they spin faster. Same person, same total angular momentum, but different distribution of mass. The closer the mass is to the axis of rotation, the faster the rotation has to be to conserve angular momentum. The farther out the mass spreads, the slower the rotation. Earth works the same way. If mass moves from the poles toward the equator, Earth's rotation slows down slightly. If mass moves from the equator toward the poles, rotation speeds up. These changes are small, really small. We're talking about milliseconds per day, but they're real and they accumulate over time. Now let's add another layer. Earth isn't a perfectly rigid sphere. It's not a solid ball of rock spinning in space. It's made of layers. There's a solid inner core, a liquid outer core, a thick mantle that behaves like a very slow-moving fluid over long timescales, and a thin crust on the surface. Each of these layers can move somewhat independently. They interact. They transfer energy and momentum between each other, but they're not locked together like a single solid object. This matters because when something changes in one layer, it can affect the others. If the outer core shifts its flow pattern, that can apply a torque to the mantle. If ice sheets on the surface melt and redistribute water, that changes the mass distribution of the crust and oceans. These internal shifts don't violate conservation laws. They just move angular momentum around within the Earth system. And as that happens, the overall rotation adjusts to balance everything out. There's another important distinction to make. We need to separate two different kinds of changes. One is a change in rotation speed, how fast Earth spins. The other is a change in axis orientation, the direction the axis points. Both can happen, sometimes together, sometimes separately, and they're driven by different processes. A change in rotation speed is usually about mass redistribution, ice melting, ocean currents shifting, atmospheric circulation patterns changing. These move mass around on the surface or within the planet, affecting how quickly Earth completes one rotation. The length of a day can vary by a few milliseconds depending on these factors. It's not much, but it's measurable. A change in axis orientation is a bit different. The axis doesn't just point in one fixed direction forever. It wobbles. It precesses. It responds to gravitational forces from the moon and sun pulling on Earth's equatorial bulge. Over thousands of years, the axis traces out a slow circle against the background stars. This is called precession. And over even longer timescales, the tilt angle itself can vary. Right now, Earth's axis is tilted about 23.5 degrees relative to its orbital plane. But that angle oscillates over tens of thousands of years between about 22 and 24.5 degrees. What we're interested in with the recent shift is a combination of these effects. A subtle change in how Earth is oriented in space, detected through careful measurement, traced back to processes happening both inside the planet and on its surface. To understand it fully, we need to know how those measurements are made, what tools scientists use to track something as abstract as planetary orientation. But before we get there, it's worth appreciating the elegance of the physics involved. Earth's rotation is governed by simple conservation laws, the same laws that apply to spinning tops, gyroscopes, and galaxies. Mass and energy move, the system responds, balance is maintained, not through some active control mechanism, but through the automatic consequences of physical laws. The planet doesn't try to conserve angular momentum, it just does. Because that's how rotating bodies work in a universe governed by these principles. This framework gives us a lens, a way to think about planetary motion that makes sense. Earth spins because it formed from a rotating cloud of gas and dust. That rotation has been conserved ever since, modified slightly over billions of years, adjusted by tidal interactions and internal changes, but fundamentally continuous. The shift we're discussing is part of that continuity, a small adjustment, a response to changing conditions, a reminder that even the ground beneath our feet is part of a dynamic system governed by elegant physical laws. So how do scientists measure something as subtle as a planetary shift? How do you detect a change in orientation when you're standing on the very planet that's moving? The answer involves looking beyond Earth itself. using reference points so distant that they appear fixed, and building networks of instruments precise enough to track motion measured in fractions of a degree. Let's start with the challenge. If you want to know how Earth is oriented in space, you need something to compare it against, something that doesn't move with Earth, something stable, permanent, far enough away that its position doesn't change from our perspective over human timescales. For a long time, stars served this purpose. Astronomers mapped the positions of stars and used them as reference points. They noticed that stars appeared to trace circles in the sky as Earth rotated. By tracking those circles over time, they could infer how the planet's rotation changed. But stars aren't perfect reference points. They move, slowly, over centuries and millennia. Their positions shift relative to each other. For precise measurements of Earth's orientation, we needed something better. Enter quasars. These are incredibly distant objects, supermassive black holes billions of light years away. They shine brightly in radio wavelengths, and crucially, they're so far away that they appear essentially motionless from Earth's perspective. Over decades, their positions change by less than the measurement uncertainty. That makes them ideal reference points, a fixed frame against which Earth's motion can be measured. Radio telescopes around the world observe these quasars, not individually, but as a network. This technique is called Very Long Baseline Interferometry, or VLBI. Multiple telescopes, separated by thousands of kilometers, observe the same quasar at the same time. By comparing the signals, scientists can determine the exact distance between the telescopes, and since those telescopes are fixed to Earth's surface, measuring their positions relative to distant quasars tells us how Earth itself is oriented in space. It's an incredibly precise technique. VLBI can measure distances accurate to a few millimeters across intercontinental baselines. It can detect changes in Earth's rotation rate down to fractions of a millisecond per day. It can track how the axis wobbles with precision better than a few centimeters. This level of accuracy transforms planetary orientation from an abstract concept into concrete, measurable data. But VLBI isn't the only tool. Scientists also use satellite laser ranging. This involves firing laser pulses at satellites equipped with reflectors. By measuring the time it takes for light to travel to the satellite and back, you can determine the satellite's exact position. And since satellites orbit Earth, their positions depend on how the planet is rotating. Combining data from many satellites over time reveals subtle changes in rotation and orientation. There's also GPS, the Global Positioning System. Originally designed for navigation, GPS satellites are incredibly sensitive to Earth's rotation. They have to be. Their signals depend on precise timing, and time is affected by both gravity and velocity, thanks to relativity. By tracking how GPS signals propagate from satellites to ground stations, scientists can infer details about Earth's rotation and orientation with remarkable precision. All of these methods generate data, lots of data, continuous streams of measurements collected 24 hours a day, 365 days a year. The challenge is combining them. Each technique has strengths and weaknesses. Each is sensitive to different types of motion. VLBI excels at measuring orientation. Satellite laser ranging is great for tracking rotation rate. GPS provides continuous coverage. By integrating all these data sources, scientists build comprehensive models of how Earth moves. But measurement is only the first step. The data has to be processed. Noise has to be filtered out. Systematic errors have to be corrected. Atmospheric effects, instrument drift, even the gravitational pull of nearby objects, all of these can introduce small biases. Removing them requires sophisticated analysis. It requires comparing independent measurements to see what's real and what's artifact. This is where international collaboration becomes essential. No single observatory or agency can do this alone. Instead, organizations around the world contribute data to shared databases. The International Earth Rotation and Reference System Service, or IIS, coordinates much of this work. They collect measurements from dozens of observatories. They run models that predict how Earth should rotate based on known physical processes, and they compare predictions to observations, looking for discrepancies. When a discrepancy shows up, that's interesting. It means something unexpected is happening. Maybe the model is missing a process. Maybe there's new physics at play, or maybe conditions have changed in a way that wasn't anticipated. The recent shift in Earth's orientation appeared as one of these discrepancies, a persistent deviation between predicted and observed rotation. Small at first, but consistent across multiple measurement systems and growing clearer over time. Here's the key. These measurements have to be continuous. You can't just take one snapshot and call it done. Earth's rotation varies on many timescales. There are daily fluctuations caused by tides, seasonal variations driven by atmospheric circulation, longer-term trends related to climate and ocean currents. To separate a genuine shift from short-term noise, you need years of data, decades even. You need to watch the pattern emerge, to see the signal rise above the background. That's what scientists did. They monitored Earth's orientation continuously. They watched as small deviations became trends, as trends became significant patterns, as patterns pointed toward a conclusion that couldn't be ignored. The planet's orientation had shifted, not dramatically, not enough to disrupt daily life, but measurably, verifiably, recorded in instruments scattered across the globe and orbiting overhead. By understanding how these measurements work, we see how abstract questions about planetary motion become concrete scientific facts. We see how precision transforms intuition into knowledge, and we see how a global network of instruments and researchers can detect changes so subtle that no human could ever feel them. This is science at its best, extending perception beyond its natural limits, making visible what would otherwise remain hidden, and revealing a planet far more dynamic than our senses alone could ever show. Now let's trace how this shift was actually discovered. How did scientists first notice something was different? And how did they confirm it was real? The story is one of careful observation, persistent anomalies, and the slow accumulation of evidence. Planetary shifts don't announce themselves. There's no moment when alarms go off, no dramatic event that marks the beginning. Instead, the discovery happens gradually. Researchers notice small discrepancies in their data, differences between what models predict and what instruments measure. At first, these differences are within the range of uncertainty, easy to dismiss as measurement error or unmodeled short-term fluctuations. But when they persist, when they show up across multiple independent datasets, they become harder to ignore. That's what happened here. Over the course of several years, scientists monitoring Earth's rotation noticed something odd. The planet's orientation wasn't behaving exactly as expected. The axis wobbled slightly more than models predicted. The rotation rate varied in ways that didn't match known seasonal patterns. The changes were small, fractions of a degree, milliseconds per day, but they were there, consistent, measurable. The first step was to check the instruments. Maybe something was wrong with the measurements themselves. Telescopes were recalibrated, laser ranging systems were tested, GPS signals were analyzed for systematic errors, but the anomalies remained. Different measurement techniques, operated by different groups in different countries, all showed similar deviations that ruled out instrumental error. If one telescope was malfunctioning, others would show different results, but they didn't. They all pointed in the same direction. Next, researchers looked at their models. Maybe the problem wasn't in the measurements but in the predictions. Earth's rotation is influenced by many factors: atmospheric winds, ocean currents, groundwater storage, tidal forces. Models attempt to account for all of these, but they're never perfect. Maybe something was missing, a process not fully captured, a variable not properly weighted. Scientists refined their models. They included more detailed atmospheric data, better ocean circulation models, improved estimates of ice mass changes. Each refinement brought the predictions closer to the observations, but not close enough. Even with the best available models, a residual signal remained. The planet was still rotating and orienting slightly differently than it should, and that residual pointed towards something real. The turning point came when multiple lines of evidence converged. VLBI data showed a shift in axis orientation. Satellite laser ranging confirmed changes in rotation rate. GPS measurements detected subtle position shifts in ground stations around the world. All of these were consistent with a single underlying change in how Earth was balanced. They told the same story from different angles. That's when confidence began to grow, when researchers started to accept that what they were seeing wasn't noise or error, but a genuine planetary shift. But accepting the shift was only the beginning. The next question was why? What caused it? What physical process could redistribute mass on a scale large enough to affect Earth's entire orientation? This is where the detective work really began. Researchers compared the timing of the shift with other known changes. They looked at climate data, ice sheet measurements, ocean temperature records, atmospheric circulation patterns, anything that might involve large-scale mass redistribution. One strong candidate emerged: ice loss from Greenland and Antarctica. Over the past few decades, both ice sheets have been losing mass at accelerating rates. Ice that was once concentrated near Earth's poles has melted and flowed into the oceans. That water spreads across ocean basins, redistributing mass away from the rotational axis. According to the physics we discussed earlier, that should slow rotation slightly and shift the axis orientation. The timing matched. The magnitude was in the right ballpark. The mechanism made sense. But ice loss wasn't the whole story. Other processes contributed too. Changes in groundwater storage as aquifers were depleted, shifts in atmospheric pressure patterns affecting how air mass was distributed, variations in ocean currents moving heat and salt around the globe. Each of these had small effects, but combined they added up. Together they explain the observed shift more completely than any single factor alone. This is typical of how planetary scale phenomena work. They're rarely caused by one thing. Instead, multiple processes interact. They reinforce each other. They create complex feedback loops. Untangling them requires data from many sources, careful statistical analysis, patience to watch patterns develop over years, and the humility to accept that even with all this work, some uncertainty will always remain. The discovery of the shift also highlighted something important about scientific knowledge. It's not static. It evolves as new data comes in. Early estimates of the shift's magnitude were rough. As more observations accumulated, those estimates became more precise. Uncertainties shrank. Confidence intervals tightened. What started as a possible anomaly became a confirmed trend. What began as a question mark became a documented fact. And here's the thing. This shift isn't over. It's ongoing. Scientists continue to monitor Earth's orientation. They watch how it evolves. They compare new measurements to updated models. They refine their understanding of the processes involved. The shift that's already occurred tells us something about what's happened over recent decades, but future shifts will tell us about what's happening now and what might happen next. By following this discovery process, we see how science works in practice. It's not about sudden revelations or single experiments. It's about accumulating evidence, cross-checking results, building consensus through independent verification, and accepting conclusions only when the weight of evidence becomes overwhelming. The shift in Earth's orientation was discovered this way, not in a moment but over years, not by one person but by a global community of researchers, not through a single measurement, but through the convergence of multiple lines of evidence, all pointing in the same direction. So we know the shift happened. We know how it was measured. Now let's dig into why. What are the physical processes driving this change? To answer that, we need to think about Earth not as a single solid object, but as a system of interacting layers. Each layer has its own dynamics, and changes in one layer can influence the others. Start with the surface. This is where the most obvious changes occur. Ice melts, water moves, vegetation grows and dies. Humans build cities and drain aquifers. All of these redistribute mass, and when mass moves on a rotating planet, the rotation adjusts. We've already talked about ice sheets. Greenland and Antarctica have lost trillions of tons of ice over recent decades. That ice became water, water that flowed into the oceans, water that spread across ocean basins far from the poles. Think about what that means in terms of mass distribution. Ice sheets are massive. They contain huge amounts of water concentrated in relatively small areas near the rotational axis. When that ice melts, the mass spreads out. It moves from high latitudes toward the equator, from concentrated piles toward distributed layers. That's exactly the kind of redistribution that affects rotation. It's like the figure skater extending their arms. The mass moves farther from the axis, and to conserve angular momentum, rotation slows down. But the story doesn't end there. Water in the ocean doesn't just sit still. It moves. Ocean currents driven by wind, temperature, and salinity differences transport water around the globe. The Gulf Stream carries warm water from the tropics toward the North Atlantic. The Antarctic Circumpolar Current circles the Southern Ocean. These currents are massive flows, billions of tons of water constantly in motion, and as they shift, they redistribute mass in ways that can affect rotation. Now add the atmosphere. Air has mass too. Not as much as water or rock, but enough to matter. High-pressure systems and low-pressure systems represent concentrations of air mass. When these pressure patterns shift, when winds change direction or intensity, the atmosphere's mass distribution changes. During El Niño events, for example, tropical atmospheric circulation patterns shift dramatically. That redistributes air mass across the Pacific, and that can have small but measurable effects on Earth's rotation. Go deeper. Beneath the crust lies the mantle, a thick layer of rock that flows very slowly over geological timescales. The mantle isn't uniform. Hot plumes rise from deep below. Cold slabs sink from the surface. Convection currents churn through the rock like extremely slow-motion boiling water. These flows redistribute mass within the planet. They're slow, really slow. But over millions of years, they shape the surface. They drive plate tectonics, and they subtly influence how Earth's mass is distributed internally. Even deeper is the outer core, a liquid layer of iron and nickel surrounding the solid inner core. The outer core is in constant motion. It generates Earth's magnetic field through a process called the geodynamo. As the core flows, it creates complex patterns of circulation. These patterns change over time. They can shift suddenly in what's called a geomagnetic jerk. When the flow pattern changes, the angular momentum of the core changes. And to conserve total angular momentum, the mantle and crust have to adjust. They rotate slightly faster or slower to compensate. All of these layers interact. They exchange energy, they transfer momentum. Changes in one layer can trigger responses in others. For example, when ice sheets melt, the land beneath them rebounds. The crust slowly rises as the weight of ice is removed. That's called isostatic adjustment. And as the crust rebounds, it slightly changes the shape of the planet, which changes how mass is distributed, which affects rotation. The same goes for groundwater. When aquifers are depleted, when water is pumped out faster than it's replenished, mass is removed from beneath the surface. That water often ends up in the oceans. So aquifer depletion is another pathway by which mass redistributes from land to sea, from high elevations to sea level, from concentrated reservoirs to spread out ocean layers. Each pathway contributes to the overall shift. Here's what makes this complex. These processes don't happen in isolation. They overlap. They interact. Ice melting affects sea level, which affects ocean currents, which affects heat transport, which affects atmospheric circulation, which affects where and how much it rains, which affects groundwater recharge. It's a web of connections, a system of feedbacks, and Earth's rotation responds to the net effect of all of them combined. This is why modeling Earth's rotation is so challenging. You can't just look at one factor. You have to account for the whole system, surface processes, deep interior dynamics, exchanges between layers, coupling between ocean, atmosphere, crust, mantle, and core. Each component has its own timescales, its own characteristic behaviors, and they all feed into the final result, the rotation rate, the axis orientation, the way the planet balances itself in space. The recent shift reflects all of this. It's not caused by one thing. It's the cumulative effect of multiple processes happening simultaneously. Ice loss is a major contributor, but ocean circulation changes matter too. So do atmospheric shifts. So does the slow ongoing dance between mantle and core. Together they create a pattern of change, a shift that's been measured, documented, understood as the inevitable consequence of Earth being a dynamic system rather than a static one. By viewing Earth this way, we see the shift not as an isolated event, but as part of continuous adjustment. The planet is always responding, always balancing, always redistributing mass and momentum among its various layers. The shift we're discussing just happens to be one we've been able to measure with unprecedented precision. It's a window into processes that have been ongoing for billions of years, a reminder that the ground beneath our feet is part of a living, dynamic system. But Earth doesn't rotate in isolation. It's part of a larger system, a gravitational environment shaped by the moon, the sun, and even distant planets. These external bodies exert forces on Earth, and those forces play a role in how the planet rotates and orients itself in space. Let's start with the moon. It's our closest neighbor, and it has a profound influence on Earth's rotation. The moon's gravity pulls on Earth's oceans, creating tides. Water on the side facing the moon gets pulled slightly toward it. Water on the opposite side gets pulled slightly away. This creates two bulges in the ocean surface. As Earth rotates beneath these bulges, the tides rise and fall. But here's the key. The tidal bulges don't align perfectly with the moon. Earth's rotation drags them slightly ahead. The friction between the rotating Earth and the tidal bulges creates a torque. That torque acts like a brake on Earth's rotation. It slows the spin down, very gradually, over millions of years, and as Earth's rotation slows, angular momentum has to be conserved. That momentum gets transferred to the moon. The moon's orbit gradually expands. It moves farther away. This process has been going on since the moon formed. Billions of years ago, Earth rotated much faster than it does now. A day was only a few hours long. The moon was much closer. Over time, tidal friction has stretched the day to 24 hours, and the moon has receded to its current distance of about 384,000 kilometers. It's still happening. Earth's rotation slows by about 1.7 milliseconds per century. The moon drifts away by about 3.8 centimeters per year. The numbers are small, but they're real, measurable, and they show how external gravitational interactions shape planetary motion. The sun plays a role too. It's much more massive than the moon, but it's also much farther away. Its gravitational pull on Earth is weaker in terms of tidal effects. Still, it contributes. Solar tides combine with lunar tides to create patterns of stronger and weaker tidal forces. During spring tides, when the sun and moon align, the combined effect is strongest. During neap tides, when they're at right angles, the effect is weakest. These variations cause short-term fluctuations in Earth's rotation, small adjustments that average out over longer periods. Then there's precession. Earth's axis doesn't point in a fixed direction forever. It traces out a slow circle against the background stars. This is caused by the gravitational pull of the moon and sun on Earth's equatorial bulge. Earth isn't a perfect sphere. It bulges slightly at the equator. The Moon and Sun pull on that bulge in a way that tries to tilt the axis toward the orbital plane, but because Earth is spinning, the result isn't a simple tilt. Instead, the axis precesses, it wobbles, completing one full cycle about every 26,000 years. This precession changes which star serves as the North Star. Right now, Polaris sits close to the North Celestial Pole, but 5,000 years ago, it was Thuban in the constellation Draco, and in another 12,000 years it'll be Vega in Lyra. The stars themselves haven't moved much, but Earth's axis has pointed in different directions. That's precession at work, a slow, steady wobble driven by external gravitational torques. There are smaller effects too. Other planets in the solar system exert gravitational pulls on Earth. Jupiter is massive and far away. Venus comes close during certain alignments. These tugs are tiny, but over very long timescales they add up. They cause subtle variations in Earth's orbit and orientation. The eccentricity of Earth's orbit changes. The tilt angle oscillates. The timing of perihelion shifts. These are called Milankovitch cycles, and they play a role in long-term climate variations. Ice ages and warm periods follow patterns that correlate with these orbital changes. Now let's tie this back to the recent shift. External gravitational forces mostly affect Earth's motion in predictable long-term ways. Tidal friction slows rotation gradually over millions of years. Precession causes the axis to wobble with a period of 26,000 years. Milankovitch cycles unfold over tens to hundreds of thousands of years. These are background processes, slow, steady, well understood. The shift we're discussing is faster. It's happened over decades. That suggests it's driven primarily by internal processes, mass redistribution on the surface, changes in ice sheets, oceans, groundwater. But here's the interesting part. External forces and internal changes can interact. They can reinforce each other or partially cancel out. When ice melts and redistributes mass, that affects Earth's moment of inertia, and changes in moment of inertia affect how the planet responds to external torques. For example, as ice sheets lose mass, Earth's equatorial bulge adjusts. The planet becomes slightly less oblate. That changes how strongly the Moon and Sun can pull on the bulge. It changes the rate of precession, not by much, but by a measurable amount. So even though the primary driver of the shift is internal, external gravitational interactions modulate the effect. They add layers of complexity to the overall picture. This interplay between internal and external forces is characteristic of planetary dynamics. Nothing happens in isolation. Earth's rotation responds to mass changes within the planet, but it also responds to gravitational tugs from outside. The two effects combine. Sometimes they align, sometimes they oppose. The net result is what we measure, and understanding it requires accounting for both. What's remarkable is how well we understand these interactions. We can model tidal friction, we can predict precession, we can calculate how orbital variations should affect climate. These aren't mysteries anymore. They're well-established aspects of planetary physics. The recent shift fits into this framework. It's an example of how internal changes occur against a background of external influences, a case study in how a planet maintains its balance while responding to forces from within and beyond. By looking at Earth as part of a larger gravitational system, we gain perspective. We see the shift not as an isolated oddity, but as part of a rich tapestry of interactions, internal dynamics, external torques, long-term trends, short-term fluctuations, all woven together, all contributing to the rotation and orientation we measure today. It's a complex picture, but it's a coherent one, and it shows how planetary motion emerges from the interplay of many forces acting simultaneously across different timescales. So we've talked about what the shift is, how it was measured, and what causes it. But there's another important piece to this story: the limits of our understanding, the things we still don't know, the uncertainties that remain even with all our data and models. Science is often presented as a collection of facts, things we know for certain, but the reality is more nuanced. Science is also about uncertainty, about knowing what we don't know, about mapping the boundaries between knowledge and ignorance. And when it comes to Earth's rotation, there are still some significant gaps. Let's start with the deep interior. We have a pretty good understanding of Earth's layers. We know there's a crust, mantle, outer core, and inner core. We know their approximate compositions, their densities, their temperatures, but the details are fuzzy. The mantle is 1,000 kilometers thick or more. We've never drilled more than a few kilometers into it. Everything we know comes from indirect measurements, seismic waves, gravity variations, magnetic field observations. These give us clues, but they're not the same as direct observation. The outer core is even more mysterious. It's liquid iron moving in complex convection patterns. Those patterns generate Earth's magnetic field, but we can't see them directly. We can only infer them from the magnetic field they produce. and the magnetic field itself is constantly changing. It drifts, it weakens in some places, and strengthens in others. Sometimes it flips entirely, with north and south magnetic poles reversing. We know this happens, we can see it in the geological record, but we don't fully understand why or when the next flip will occur. This matters for understanding rotation because the core carries significant angular momentum. Changes in core flow can affect how the mantle rotates, but modeling core dynamics is incredibly difficult. The equations are complex, the timescales are long, the data is limited, so predictions about core mantle coupling remain somewhat uncertain. We know it happens, we know it matters, but quantifying its exact contribution to rotational changes is hard. The same goes for long-term climate-driven mass redistribution. We can measure ice loss today. Satellite data gives us precise numbers for Greenland and Antarctica, but projecting that forward is challenging. How much ice will melt in the next decade? The next century? That depends on future climate, which depends on greenhouse gas emissions, which depends on human behavior, which is fundamentally unpredictable. Even measuring current changes has uncertainties. Satellites measure ice mass loss by detecting changes in gravity. As ice melts, the local gravitational field weakens, but gravity signals can be influenced by other processes too. Groundwater changes, tectonic uplift, sediment transport. Separating ice loss from these other effects requires careful modeling. The results are good, but not perfect. There's always a margin of error. Then there's the problem of coupling between different systems. We know the atmosphere, oceans, crust, mantle, and core all interact, but modeling those interactions is complex. The atmosphere operates on timescales of days to years, the ocean on timescales of years to decades, the mantle on timescales of millions of years, the core somewhere in between. Coupling processes that operate on such different timescales into a single coherent model is a major challenge. Current models do a pretty good job. They can predict Earth's rotation rate to within milliseconds per day. They can track axis orientation to within a few centimeters, but they're not perfect. Discrepancies remain. The recent shift is one example. It wasn't fully predicted by pre-existing models. Only after it was observed did researchers refine models to account for it. That's normal in science. Observations lead to better models. Better models make new predictions. Those predictions get tested. The cycle continues. But it also means we're always playing catch-up to some extent. Earth is a complex system. It surprises us. It does things we don't fully anticipate. And when it does, we have to update our understanding. This isn't a failure. It's how science progresses. But it does mean that uncertainty is always present. We can't predict the future with perfect accuracy. We can make informed estimates. We can bound the possibilities. But there will always be unknowns. Another source of uncertainty is human activity. Humans are now a major force in reshaping Earth's surface. We've built dams that store massive amounts of water in reservoirs. We've drained aquifers. We've deforested large regions and irrigated others. We've changed river flows. All of this redistributes mass, and all of it affects rotation. But human activity is hard to model. It changes rapidly. It's driven by economic, political, and social factors that aren't part of standard geophysical models. For example, the Three Gorges Dam in China holds about 40 billion tons of water. That's enough to measurably affect Earth's rotation. When the reservoir filled, it moved mass from distributed ocean water to a concentrated location at a specific latitude. That changed Earth's moment of inertia. It slowed rotation by a tiny amount. Scientists calculated this effect. They measured it, and it matched predictions. But anticipating where and when the next massive reservoir will be built is impossible. Future changes depend on future decisions. The same goes for groundwater extraction. As populations grow and agriculture expands, more water is pumped from underground. That water ends up in rivers, oceans, or the atmosphere. Mass moves, rotation adjusts. But predicting future extraction rates requires knowing future agricultural practices, population distribution, and water management policies. These aren't physical constants, they're human choices. So here's what we're left with. A good understanding of the basic physics, solid measurements of current behavior, models that work pretty well most of the time, but also significant uncertainties, gaps in knowledge about the deep interior, limitations in predicting future climate and human activity, challenges in coupling processes across different timescales. These uncertainties don't invalidate what we know. They just frame it. They remind us that even with all our tools and data, Earth still holds surprises. The recent shift is one of those surprises. It was bigger than models predicted. It happened faster than some expected. And explaining it fully required refining our understanding of how ice loss, ocean circulation, and other factors combine to affect rotation. That refinement is ongoing. New data continues to come in. Models continue to improve, and our understanding continues to evolve. This is actually exciting. Uncertainty isn't a problem to be solved and forgotten, it's a frontier to be explored. Every gap in knowledge is an opportunity to learn something new. Every discrepancy between prediction and observation points toward processes we don't fully understand yet. The shift we're discussing is a guide. It's telling us where to look next, what to measure more carefully, what processes to model in greater detail. By acknowledging these limits, we're being honest about what science can and can't do. We can measure planetary motion with incredible precision. We can explain much of what we observe, but we can't predict everything perfectly. Earth is too complex, too dynamic, too full of interacting processes operating on different timescales. That complexity is what makes it fascinating, and what keeps scientists working to understand it better. Now let's zoom out. Let's place Earth's shift in a broader context. Because what's happening to our planet isn't unique. It's part of a pattern that extends across the universe. A pattern governed by the same physical laws we've been discussing. A pattern that connects Earth to other planets, moons, stars, and galaxies. Start with our solar system. Earth isn't the only planet whose rotation changes over time. Mars, for example, has experienced similar shifts. Its axis tilt varies more dramatically than Earth's. Because Mars lacks a large stabilizing moon, over hundreds of thousands of years, Mars's tilt can swing by tens of degrees. When the tilt is larger, polar ice melts more aggressively. When it's smaller, ice accumulates. These changes affect atmospheric circulation, surface temperatures, and even the potential for liquid water. Mars' rotation tells a story of a planet constantly adjusting to changing conditions. Venus rotates in the opposite direction from most planets. It spins backward, and it does so incredibly slowly. A day on Venus is longer than a year. Scientists think this unusual rotation might have resulted from a massive impact early in the planet's history. Or perhaps it's due to atmospheric tides. Venus has a thick atmosphere that creates strong pressure patterns. Those patterns can exert torques on the surface over long periods. Either way, Venus shows how rotation isn't fixed at formation. It can change dramatically over a planet's lifetime. Look at Jupiter. It's a gas giant. No solid surface, just layers of hydrogen and helium in complex flows. Jupiter rotates faster than any other planet. A day there lasts only about 10 hours, but that rotation isn't uniform. Different atmospheric bands rotate at different speeds. The equatorial region spins faster than the poles. This differential rotation creates the bands and storms we see in Jupiter's atmosphere. It's a vivid example of how rotation and internal dynamics are intimately connected. Saturn's moon Enceladus provides another fascinating case. Enceladus is tiny, but it has geysers that shoot water vapor into space. But water comes from a subsurface ocean beneath its icy crust. The mass loss from those geysers is small, but over millions of years it redistributes mass, and that could affect how Enceladus rotates. It's a miniature version of what happens when Earth's ice sheets melt. Different scale, same principles. Go beyond our solar system. Consider exoplanets. Thousands of planets orbiting other stars. Many are tidally locked to their host stars. That means they always show the same face to the star, just like the moon always shows the same face to Earth. Tidal locking is an end state of tidal friction. The planet's rotation slows until it matches its orbital period. Once locked, the rotation is stable, but getting there requires the same process that's slowing Earth's rotation: tidal forces, energy dissipation, angular momentum transfer. The physics is universal. Stars rotate too. Our sun spins once every 25 days at its equator, but like Jupiter, different parts of the sun rotate at different rates. The poles rotate more slowly. This differential rotation powers the solar magnetic field. It drives solar activity, sunspots, flares, coronal mass ejections. All of these emerge from the complex interplay between rotation and internal flows. The sun is a giant ball of plasma. It doesn't have ice sheets or oceans, but it has convection. It has magnetic fields. It has processes that redistribute angular momentum, and its rotation responds accordingly. On an even larger scale, galaxies rotate. The Milky Way spins once every 200 million years or so, but not uniformly. Stars closer to the galactic center orbit faster. Stars farther out orbit slower. This creates the spiral arms we see in many galaxies. And just like planets, galaxies can change their rotation over time. When galaxies merge, their rotational patterns combine. Angular momentum is redistributed. New structures form. It's planetary dynamics played out on a cosmic scale. Here's the point. Rotation is a fundamental property of nearly every object in the universe, from planets to stars to galaxies, and in almost every case rotation changes over time. It responds to internal processes, to external forces, to the flow of mass and energy. What we've observed in Earth's recent shift is an example of a universal phenomenon, a specific instance of general rules. This perspective is humbling. It shows that Earth, for all its uniqueness, is also part of a larger pattern. The physics that governs our planet's rotation governs everything else too. Conservation of angular momentum, gravitational interactions, energy dissipation. These aren't special rules for Earth. They're laws of nature that apply everywhere. By understanding Earth's shift, we're also understanding something about how the universe works. It's also empowering, because it means the tools we've developed to study Earth can be applied elsewhere. The techniques for measuring rotation, the models for predicting change, the frameworks for understanding mass redistribution, these are transferable. They help us interpret observations of other planets. They guide our search for life on exoplanets. They inform our understanding of how stars evolve. Knowledge gained from studying one system illuminates others. And there's beauty in this unity. The same equations describe a melting glacier on Earth and a convective current in a distant star. The same principles explain tidal locking around an exoplanet and the slowing of Earth's rotation by the Moon. The universe is vast, diverse, full of unique phenomena, but it's also connected, governed by a small set of fundamental laws that manifest in countless ways. Earth's shift becomes more than a local curiosity. It's a window into universal processes, a case study in planetary dynamics that echoes across space and time. By studying our own planet, we're also studying the cosmos, and by understanding the cosmos, we better understand the ground beneath our feet. It's a loop, a feedback between local and universal, between specific observation and general principle, and it's one of the most satisfying aspects of science. When we look at Earth's changing rotation in this light, we're not just learning about one planet, we're learning about how rotation works as a universal phenomenon, how angular momentum shapes everything from dust grains to galaxy clusters, how balance is maintained through constant adjustment rather than rigid permanence, and how the laws of physics connect disparate objects across unimaginable distances into a coherent, understandable whole. So let's bring this back to the human scale, back to the question of what this shift means for us, for how we think about the world, for how we relate to the ground we stand on, and the planet that carries us through space. A planetary shift doesn't change your daily life. The sun still rises in the east. The seasons still follow their patterns. Your GPS still works. Your clocks still keep time. To your senses, nothing is different. And yet, something fundamental has changed. The orientation of the entire planet, the speed of its rotation, the way it balances in space. These aren't trivial things. They're planetary scale adjustments. They reveal processes operating far beyond immediate perception. There's something profound in knowing this, in understanding that the apparent stability we experience is, in fact, a kind of dynamic equilibrium, a balance maintained not through rigidity, but through constant response. Earth adjusts, it adapts, it redistributes mass and energy to maintain its spin, and it does this automatically, not through conscious effort, not through active control, but through the simple operation of physical laws. This challenges the old notion of a fixed, unchanging world, a solid foundation that never shifts. That notion was always an illusion, but it was a comforting one. It made the universe feel stable, predictable, safe. Learning that Earth's rotation can change disrupts that comfort slightly. It reminds us that even the ground is in motion. Even the planet is dynamic. Nothing is truly static. But here's the thing. This realization doesn't have to be unsettling. It can be empowering instead, because it shows us that stability doesn't require permanence. Earth has been rotating for billions of years. Its rotation has changed countless times. It's been slowed by tidal friction, adjusted by ice ages, perturbed by asteroid impacts, and yet it's still here, still spinning, still supporting life. Stability emerges from flexibility, from the ability to adjust and adapt, not from rigid unchangeability. Think about it in terms of balance. If you stand on one foot, you don't stay perfectly still. You sway, you make tiny corrections, your muscles adjust constantly to keep you upright. That dynamic balancing is more stable than trying to freeze in place would be. The same principle applies to Earth. The planet maintains its rotational balance through continuous small adjustments, and that's what makes it stable over long timescales. This perspective also highlights the interconnectedness of Earth's systems. Ice melts, water flows, ocean currents shift, atmosphere circulates, deep interior convex. Each of these processes affects the others. They're coupled, they form a web of interactions, and Earth's rotation is the sum of all these interactions. It's an emergent property, a result of the whole system working together. Understanding this changes how we see ourselves in relation to the planet. We're not separate from Earth's systems, we're part of them. Human activity redistributes mass, dams, irrigation, aquifer depletion. These affect rotation, in measurable ways, small ways but real ones. We've become a force in the planetary system, not the only force, not even the dominant force in most cases, but a force nonetheless, and that comes with responsibility. It also comes with humility, because despite being a force, we're still subject to the same laws that govern everything else. We can't choose to override conservation of angular momentum. We can't opt out of gravitational interactions. We operate within the constraints of physics just like ice sheets and ocean currents do. Our influence is real, but it's bounded by natural law. There's also something deeply human about the whole story we've traced. The shift itself is a natural phenomenon, but discovering it required human curiosity, human ingenuity, the drive to measure what can't be felt, to detect what can't be seen, to understand what lies beyond direct experience. We built telescopes, we launched satellites, we developed mathematical models, we collaborated across continents, all to answer a question that doesn't affect daily survival, that doesn't put food on the table or shelter over our heads. Why do that? Because we want to know. Because understanding the world satisfies something deep in human nature. Because knowledge for its own sake has value. The shift won't change how we live, but knowing about it changes how we think. It expands our mental model of what's possible. It reminds us that reality extends far beyond perception, and it connects us to a larger story, a story about planets and rotation, and the laws that govern them. In that sense, the shift is a gift, a reminder that the universe is both knowable and surprising, that we can understand things we can't directly sense, that what seems permanent can change, and that change doesn't mean chaos, it means adjustment, adaptation, the ongoing conversation between a planet and the forces that shape it. Quick question for you. If you could measure any aspect of Earth's motion, what would you choose? Rotation? Orbital path? Magnetic field drift? Let me know in the comments. I actually read them. So where does this leave us? We've followed a thread from the initial discovery of a planetary shift through the physics that explains it, the measurements that confirm it, and the broader context that gives it meaning. We've seen how Earth's rotation responds to internal and external forces, how ice, water, atmosphere, and deep interior all contribute to the planet's balance, and how that balance is maintained through continuous adjustment rather than rigid unchangeability. The shift itself is small, measured in fractions of a degree, milliseconds per day, changes that accumulate over years and decades but remain invisible to everyday experience, and yet it's significant. It tells us something important about how our planet works, about the limits of our current models, about the processes we still don't fully understand. It's a frontier, an edge of knowledge where observation meets theory, and both are refined. What makes this story compelling isn't just the science, it's also the human dimension, the teams of researchers monitoring instruments around the world, the careful analysis of data streams, the patience to watch patterns emerge over years, the collaboration required to combine measurements from different systems, and the humility to accept when observations don't match predictions, when models need updating, when uncertainty remains even after decades of work. This is science in practice, not a collection of settled facts but an ongoing investigation, a conversation between humans and nature. We ask questions, we build tools to measure, we interpret what we find, and we adjust our understanding accordingly. The recent shift in Earth's rotation is part of that conversation. It's nature saying, here's something you didn't fully expect, and science responding, let's figure out why. In a way, this mirrors our relationship with the planet more broadly. Earth doesn't exist to be convenient for us. It doesn't operate on human timescales or according to human preferences. It's a physical system governed by universal laws. It responds to forces. It redistributes mass and energy. It maintains its own balance. Our task isn't to control it or fix it in place. Our task is to understand it, to learn how it works, and to adjust our behavior accordingly. The shift reminds us of this. It shows us a planet in motion, a world that's always changing, always adjusting, always finding new equilibria as conditions shift. That's not a bug, it's a feature. It's how complex systems maintain stability over long periods, through flexibility rather than rigidity, through response rather than resistance. And there's something hopeful in that, because it suggests that Earth is resilient, not in the sense of being unaffected by change, but in the sense of being able to adjust to change, to find new balance points, to continue functioning even as conditions evolve. This doesn't mean we can do whatever we want without consequences. Changes in ice mass, in ocean circulation, in atmospheric composition, these have effects. They redistribute mass, they affect rotation, they influence climate, and those influences matter. But it does mean that the planet isn't fragile in the way we sometimes imagine. It's not a delicate mechanism that breaks if disturbed. It's a robust system capable of absorbing and responding to change. Our responsibility is to understand those responses, to anticipate consequences, to make informed choices about how we interact with Earth's systems. Knowledge is the foundation of that responsibility, and the shift we've been discussing is a piece of that knowledge. Looking forward, scientists will continue monitoring Earth's rotation. They'll refine their measurements, they'll improve their models, they'll track how the shift evolves over time, and they'll learn more about the processes driving it. Each data point adds to our understanding. Each refinement brings us closer to a complete picture, not a final answer. Science doesn't really have those, but a progressively better approximation of how Earth works. This work matters. It helps us understand climate change. It informs projections of sea level rise. It reveals connections between different parts of the Earth system. It tests our theories of planetary dynamics. And it satisfies our curiosity about the world we live on. All of that is valuable. All of it contributes to human knowledge. And all of it emerges from the simple act of paying attention, of measuring carefully, of thinking deeply about what observations mean. The shift in Earth's orientation is ongoing. It didn't stop once we noticed it. It continues now. As ice melts, as oceans move, as the deep interior churns, the planet adjusts. It finds new balance. And we watch, we measure, we try to understand. That's the relationship between humans and Earth's motion. Not control, not mastery, but observation, understanding, and ultimately, appreciation for the elegance of a planet that maintains its spin through constant adjustment, through dynamic equilibrium, through the beautiful operation of physical law. If you liked this journey through planetary motion and what a shifting world means, share it with someone who'd enjoy thinking about these questions. And if you want to explore more about how Earth works, there's another video waiting for you. Thanks for watching, and keep looking up.